Okay, in this video we're going to work on calculating the energy and the power, total energy, and average power over all time of continuous time signals, CT. So we're going to look at these three signals here, this triangular pulse, this DC signal, and this kind of ramp, they call this, a ramp. Okay, but first let's look at we'll call this example 1, our triangular pulse. Now, all three of these signals are real. The triangular pulse is a real signal, so it takes real values. So, on this part of the triangle, it takes values between 0 and 1. And then on this part of the triangle, it takes values between 1 and 0. And then over here, it's 0, and over here, it's 0. So those are real, real numbers. They're not complex. And so what I can do right away is if I want to calculate the total energy, I can remove the absolute value. If you remember, the absolute value was a fail-safe for when the signal was complex. Okay, so I'm going to remove the absolute value, and I need to perform this integration. And so I'm going to have to model my pulse with some mathematics. And that is to say, I'm going to come up with the equation of this line here. So the one on the right has a slope of -1 and an intercept of 1. And remember, the independent variable here is t. So a slope of -1 and an intercept of 1, that means this function on the right is 1 minus t. And on the left, similarly, this has an intercept of 1, but a slope of 1. And so on the left, that's 1 plus t. Now that doesn't go on forever, certainly, right? These lines don't extend towards infinity. So this 1 minus t, that's only valid in the range t goes from 0 to 1, in this range here. And this function 1 plus t, that's only valid from -1 to 0. Outside of that range, the signal is 0. So it has no energy there. So I can kind of forget about that in my integral. So I'm going to write this integral as two pieces from -1 to 0 of 1 plus t quantity squared dt. Right, so that's the piece on the left, plus the integral from 0 to 1 of the piece on the right, which is 1 minus t squared dt. And if you're really up on your mathematics, yes, you can actually just calculate the energy in 1/2 of that triangle and then double it at the end. And that would give you the right answer. So, but we're going to work it out the long way, and we're going to see if each one of these pieces gives us the same energy, and it should. Okay, so now we can work that out, right? So I can expand the 1 plus t squared. That gives me 1 plus 2t plus t squared. Okay, and then the next integral gives me 1 minus 2t plus t squared dt. Okay, and again, I want to point out, you say, well, where did the infinities go? The integral from -infinity to -1, not shown here, is going to be 0 because the signal is 0. So I just left it off. And the piece from 1 to infinity, I've also left off. That's going to give us 0 too because the signal is 0. Okay, so now we need to integrate this. So this gives me the 1 becomes a t. Then I have plus t squared plus 1/3 t cubed from -1 to 0. Right? I guess looks like this, plus, then integrate the second piece, that's a t minus t squared plus 1/3 t cubed from 0 to 1. Okay, and now I plug in my bounds here. Now notice when I plug in 0, I get 0. And when I plug in -1, so minus what I get when I plug in -1, I get a -1, then a +1, then a -1/3. And that's in the first piece. Feel free to pause this video if you need to. Work out these details yourself. Then in the second piece, okay, plug in the 1. That's a 1 minus 1 plus 1/3. And then when I plug in 0, I get 0. And so notice here on the first piece, the -1 and the +1 cancel, and I get 1/3. And then on the second piece, I also get 1/3, right? Remember when we started this, we said we could double whatever we get for the left side or the right side. And so we get an energy of 2/3. So that would be our answer for the energy. And now if we wanted the power, the average power over all time, remember that's the limit as this capital T goes to infinity of 1/2t times the integral minus t to t of the absolute value of x of t squared. Now, this is, of course, related to the energy, which we just calculated. This is the limit as t goes to infinity of 1/2t times the limit as t goes to infinity of that integral. And the reason I'm writing it that way is because this second piece here, you see, that is what we just calculated. That's 2/3. As t goes to infinity, we go from minus infinity to plus infinity of the absolute value of the signal squared. That's 2/3. And so what we get is the limit as t goes to infinity of 2/3 over 2t. So what is that limit equal to? As t goes to infinity, we have a finite number divided by something that goes to infinity. That limit is 0. That is our power averaged over all time. So that was example 1, right? And that was one of those classes that we had on the previous video. So I'm deleting that quickly, but feel free to go back and take a look on your own. Pause the video or whatever you need to do. All right, now let's look at example 2. Example 2 is a DC signal. It never changes and it goes on forever. So let's calculate its energy. That's the integral from minus infinity to plus infinity. And this is a purely real signal. It's just 1. So 1 is certainly real, so I can leave off the absolute value. And so 1 squared is just 1. And I'm not even going to write the 1. I'm just going to write dt. So here's my integral now I have to evaluate. So when I integrate dt with respect to time, I get t plugged in from infinity, from minus infinity to infinity. So this is improper. This is infinity plus infinity, right? This is twice infinity, so that goes to infinity. Infinite energy. But let's take a look at its power, averaged over all time. This is the limit as this capital T goes to infinity of 1/2t times minus t to t of, and again, it's purely real and it's 1, so I'm just going to write dt here. Okay, so now let's consider this. Okay, so I've got this guy here, and when I integrate, I get t. t. And I'm going to plug in minus t to plus t capital. Okay, and so what I get is t when I plug in the top bound minus t when I plug in the bottom bound. So this is 2t, that cancels with the 2t. So actually I have the limit as t goes to infinity of 1. So that's just 1. So this is the second class of signal where the energy over all time is infinite, but the power averaged over all time is finite. All right, and finally, let's look at our third example down here, this ramp function. So I'm just going to write it down here. Again, our signal over all time, I'm going to model this with mathematics. So I need the equation of this thing here. Right? Well, it goes through the origin and has a slope, we're told, of 1. So this is just x of t equals t. X of t equals t. But it doesn't extend on forever, right? It starts at the origin. So that x of t equals t is only valid from t goes from 0 to infinity. So over here, from minus infinity to 0, the signal is 0. And so it has 0 energy, and so I'm just going to leave it off. So I'm going to start my integral from 0 to infinity, like that. And what am I going to integrate? Well, I'm going to integrate, this is purely real, and so I can leave off the absolute value, and then I'm going to square it. So this is t squared dt. By the way, this was a sad face. And I'm also going to get a sad face here because I'm sad that my integral doesn't converge. This is 1/3 t cubed evaluated from 0 to infinity. So when I plug in infinity, this thing blows up. This is infinity cubed over 3, and then minus 0. So this is also sad face. And that's infinite power. Infinite energy. All right, let's look at the power now, which is the rate of the energy. So this is limit as some t goes to infinity of 1/2t. And I'm going to write it like this again. Oh no, I guess we'll keep it, we'll just so we can compare it, we'll do the exact same steps we did before. Minus t to t, and again what I have here is t squared, so this is again x of t equals t, and then we square it. Okay, so now I've got 1/2t, and this integral is 1/3 t cubed. From minus t to plus t. And so this is the limit as t goes to infinity of 1/2t times, now I plug in capital T, this gives me 1/3 t, capital T cubed, minus, and then, so that makes a plus 1/3 capital T cubed, like that. Again, feel free to pause the video, do what you need to do. But now notice I've got 1/3 t cubed and 1/3 t cubed, so that's 2/3. And then the t cubed, one of the cubes, or one of the t's cancels with the bottom t. And so this leaves me with the limit as t goes to infinity of t squared over 3. Okay, and so everything's reduced here. So what is that limit? Well, t goes to infinity. So that limit is infinity. Oh, and I'm sad because I didn't get a number. And so this is that third class of signal where the energy over all time is infinite and the power averaged over all time is also infinite.